Okay, I appreciate your patience, everybody. Thank you. And I really hope I can do this in under 5 hours. Let's see how it goes. Um, so, the last time we talked a little bit about journal bearings. This time we're going to talk about rolling element bearings. These kind of come in two different flavors, either ball bearings or so like a cylindrical or a conical roller bearing. And I'll show you some pictures of those coming up. And all right. So a little bit of nomenclature. I think we might have talked about this last time, but there is, the number one thing you're really interested in is the bore here, right? So because this has to fit your shaft size, um, because that goes in the bore, right? And then where does this thing sit, right? It sits in something else. So your outer diameter is kind of the other key um, dimension. All right. One more really important one here is this corner radius, right? So why do we have this? That's absolutely critical because then when we're machining steps or other ways to hold this thing in place, we'll talk about this more in a couple weeks. This is for fillets um, and KF reduction, right? Because we don't want a sharp corner on our shaft. Consequently, we have to have a radius machined into the bearing here. All right. So there's the inner ring, the outer ring, and then the balls actually roll on a race. There's an inner race here, right? This thing here is the inner race. This surface that they roll on, this outer surface here, is the outer race, and then this is the um, retaining clip or the separator, right? So there's a this and this is a very loose fit, but it just kind of maintains the spacing of all the balls between the two um, rings. Okay, so that's kind of the basics of that's a basic deep groove ball bearing, right? As I mentioned, there's several types of ball bearings. There's the deep groove. The filling notch means that it's big enough here. Typically, there's only one filling notch where I kind of offset the rings, and then I can get the ball in there. Angular contact bearing, we can see that this doesn't actually show it very well. We'll skip that. A bunch of other ones, right? The shielded means there's just some sort of little clip here that prevents stuff from getting in. This is sealed, where it's shielded, and it has some sort of rubber seal to keep. This will keep dust out. So this is good for dust. This is good for dust and maybe some rainwater. These are not really submergible. If we tried to submerge these, they would get wet. Self-aligning, this is what we've talked a lot. We say, okay, assume it's self-aligning bearings, assume it's self-aligning bearings. Because what can happen is, this can tip relative to this, right? So where it mounts on the outside, and then so this whole thing can rotate in here. So this could tip this way or this way. So um, so that would not provide a resistance to moment, whereas this would, right? We don't want to do that because that puts undue stress on the bearing, but this can freely slip. Double row, self-aligning. A thrust bearing is where the load goes like this, right? These other ones are all made, so this is P and then P. And then, this is for a radial load, right? Here's the center line. This is radial load. Here's the center line here. Here's the load that kind of compresses the bearing that way, all right? Roller bearings. The other day I talked about, or in a little bit, I'm going to talk about some trailer bearings. In reality, most wheel and most wheel bearings look like this, whether they're on a car or a trailer or a tractor or something like that. These would be a tapered roller bearing. The reason being is that they're pretty low profile in this direction. So they're small in this direction here. And they have a very large surface area, right? So if you think about the contact stresses, That's pretty low. Some specialty cases, needle bearing, which is really just a roller bearing, but with really, really small fat needle, small, long, thin rollers, right? And so we call them needles. For the purposes of our design project, we're going to be working strictly with ball bearings. All right, now this is always a little confusing to me. So basically, I think this is a pretty good schematic. It comes from our book, right? So let's say I know the size of the shaft, right, and it's whatever this dimension, and the more load I need to carry, the bigger bearing I need, right? So the medium series would carry a very high load. The light series would carry this. So this is extra light, or this is extra extra light. This is light. Light series is 200. Medium series is a 300 series bearing, right? So as the bearings get heavier, the inner diameter, or the bore, stays the same. Remember, this dimension is called the bore. So we'll call that the bore there, right? The outer diameter is going to get bigger as they need to get heavier and heavier, or stronger and stronger bearings. The same thing is true over here, but let's say for some reason I have to fix the outside diameter. As I have bigger and bigger loads, the bore needs to get smaller and smaller and smaller. So this is the outside diameter here, OD. Right. So this is just a good visual, right? Extra light bearings. Basically, the smaller the balls, the smaller the load. Why is that? Because I know that surface stresses are related to radius, or inversely related to radius. So the larger the radius is here, the less the surface stresses are, the contact stresses, the Hertzian stresses. Okay, so that's a little bit of that. All right. Keeping the dirt out of the bearings, that is important. So there's two types. I talked about this briefly already. We've got shielded bearings and then sealed bearings. This may seem like, oh, well, why wouldn't I use a seal every time? Because when you put the seals in here, the rubber seals tend to generate a lot of extra friction, right? So these things don't spin quite as well. Okay. So they cause some extra friction. All right, let's take a quick look here, see if I can get this to work. So this is the little ball bearing that I showed you the other day, right? We're going to look at this again in a little bit. You can see this has a little shield on it, right? And this is basically a skateboard wheel bearing, but this has just a shield on it right there to keep this stuff out. Okay. So if I spin this, it doesn't really spin like a fidget spinner would spin. It doesn't keep spinning for a long time. So one example there. All right, anyway. Whoops, what's next here? I need to go back to here. And again, some bearing dimensions that we're pretty interested in. Let's say we have, this is the shaft that is either the outer part is rotating or the inner part is rotating. Let's say the shaft rotates. And then this is fixed, right? And so here we can see that little radius, right? So this radius here reduces, F, the fatigue stress concentration factor. And then we have the bore and then the OD, right? And notice there's all sorts of little shoulders and stuff built into this in order to hold everything in place, right? So diameter of the shaft, diameter of the housing. So this is housing, like that. And then the bearing allows these two things to move independently. This may seem redundant, but for those of you who haven't looked at bearings a lot or spent a lot of time playing with them, probably another nice little good schematic to see. All right, now we have to talk about what defines the life of a bearing. All right, and so how do these things fail? Typically due to surface contact, surface fatigue, right? So it's spalling or pitting of an area greater than 0.01 inch squared, right? So that's pretty small. It's 1/10 of an inch by 1/10 of an inch. And if that happens, then things go downhill fast because there's all sorts of impacts and contacts and stuff like going on. Life is given in the number of revolutions, right? and this should seem obvious here, that we can't really say hours, or if we said hours, we'd also have to give a speed, or if we gave like years or weeks or whatever, we'd have to really rate that to something else. So we typically refer to it in um, just the number of revolutions. All right, the rated life. This is important. The rated life is for 10% of the samples to fail. Okay, so this is called L10, right? And that's for 10% of the samples to fail. The median life. So this is also corresponds to 90% reliability. All right. And then the median life, right, is the average life required for 50% of the samples to fail. Okay, so this is 50% reliability. And then I guess I make note of this later. The median life is typically 4 to 5 times the L10 life. Does that make sense? Yeah, sure. If only 10% of them fail, um, that will be before 50% of them fail, right? So I have 100 bearings running. When the 10th one fails, I say, okay, that's L10. And then when the 50 of them fail, then I call that the median life. Right? So that's important to know that L10 is the 90% reliability. All right. More on this. The catalog rating, right? The catalog load rating. All right. So this is C10, right? And that's the constant radial load. All right. So if this is my bearing, like this, and then there's, of course, another one down here. That's this load here. Right. So that's a radial load. Right. So the constant radial load that causes 10% of a group of bearings to fail at the bearing manufacturer's rated life. Okay, so the load and the life are related here, and it's yeah, okay, I'll get to that next. But it really, so this is the big one here is accuracy of fabrication, right? So how carefully are these things manufactured? Of course, materials matter. A roller bearing is going to have a totally different life, totally different load rating than a ball bearing, whatever, right? Okay. Now the basic load rating, all right. What does this mean? So remember, this is a load rating. So the basic load rating C is a catalog load rating based on a rating life of 10 to the 6th revolutions of the inner ring. All right, so what load would cause 10% of these to fail? And here's the key thing. After 1 million cycles. Right? So that is C10, right? C10 is the catalog load rating. Now, usually, I better make note of that. So how do I change colors here? Whatever. I can't change colors. So it's important to know here that this is typical. Right. I don't spend a lot of time looking at bearing catalogs, quite frankly, but everyone I've ever seen have all been based on 1 million cycles. All right. But why is this thing in red here? The basic load rating is a reference value, not an actual load. It's a reference value, not an actual load. That doesn't make any sense. Let's see what that. Okay, so the static load rating, C0, right? That's the static radial load. Okay, radial load, we've talked about that, which corresponds to a permanent deformation of rolling element and race at the most heavily stressed contact of 0.0001 D. All right. So what is the little d? Again, so if I've got a a deep groove roller bearing that looks something like this, right? Remember the center line is down here somewhere. So this is D, right? This is the diameter of the rolling element right there. So 0.0001, that's 1/10,000th, right? 0.0001D. That's tiny, right? Um, if we look at this one, right, you can kind of estimate, what the size of the ball in there might be, and we're looking at 1/10,000th of that. All right, so that's a tiny, tiny, tiny deformation. But all it takes is one little surface crack or one little surface pit, and this thing really kind of stops working. Okay, and then finally we have the equivalent radial load, right? That is, okay, let's go back to this one. For instance, if this was a skateboard bearing, you see sometimes when we were in Costa Rica, we saw these guys skating down these insanely long and steep mountain roads. I mean, just crazy. But they do they try to burn off speed by sliding sideways on their skateboard. So that puts a big axial load on this bearing, right? So somehow we have to combine an axial load and a radial load with to some equivalent load to help calculate life. And so the equivalent radial load is a combination of loadings put into one, right? We've seen that before with stresses. All right, so here's some typical bearing data, right? This is not from our book. This is from a different book, but I like it because it gives us, so the bore, right, that's the inner diameter. The outer diameter, the width, it gives us the radius and all this stuff. But then it also gives us load ratings, right? C10, right, that's the load to get 10% of them to fail after a million cycles. Right, and then C0 is the load to just deform it once, right? I just load this thing up once and it fails. All right, so let's look at a typical bearing here. Now, I know it's painful. You're watching a PowerPoint video online. You're stuck in your parents' basement, wherever you are. And now, not only that, but I'm going to throw some table in. But let's take a look. All right. So here is um, a 40 millimeter bore, right? So that's pretty big. What would 40 millimeters look like? So let's open this up to 40. So this is what we're talking about, right? This is a 40 millimeter bore. So that's a pretty big thing, right? So that's like a truck axle or maybe a 20,000 pound trailer axle or something like that. Okay. So that's that, and then let's go back. So the outer diameter is 8 times. Oops. The outer diameter is 8 times that, 18 millimeters wide. Fine. Fillet radius 1, whatever. It's got some shoulder diameters. Blah 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 blah. All right. Load ratings. This is in kilonewtons. Let's remember that this is in kilonewtons here. What is a kilonewton? Right. Doesn't show up red on pink. Not so great. The C10. So at a load rating. With a load of 30.7 kilonewtons. So 30.7 kilonewtons is 30,000 newtons, right? Which is ballpark 8,000 pounds, right? Okay, 8,000 pounds. Yeah, that's a big truck axle, so that makes about sense. Okay, so it can carry that. And then how much load would it take to damage it? 16 kilonewtons. Does that make sense? Hold on. This says, according to this, it'll last for, I can put a 30 kilonewton load on this thing and run it for a million cycles. But according to this, if I put 16 kilonewtons on it, the bearing fails statically. What? All right, that's crazy. Hold on. Oh yeah, the basic load rating is a reference value, not an actual load, right? So if you tried to load this thing up to C10, right, it would fail right away, right? Why is that? Because bearings are designed to last many, many more times than a million revolutions, right? And so we'll see how this relationship works between bearings and the life of the bearing and the load of the bearing. Hold on, I got to turn off the furnace. Okay, so it doesn't make sense that C10 could be more than C0. but it actually kind of does, right? It's just a reference value. So relationship between the load F, right, and the life L. Now, would it make sense to use L for load and L for life? Yes, except that we can't. So bear with me here that load rating is C, load is F, and life is L. All right. So if we were to plot these on a log-log scale, again, we would discover that there's a linear relationship between um, the F, what is F again? The load and the life, right? So the higher the load, the shorter the life. A lower load leads to a longer life. That makes sense. Let's write down. Smaller load. Adjust my pen here. Smaller. Whoa. Load equals longer life. I don't know what's going on with my pen here. Something's really going on with my pen. Okay. All right. And so now we're going to say that the relationship is like this. It's exponential or logarithmic. So the load, right? We better label that because that gets confusing. So remember that this is the load, and this is the life. And I don't know what's going on with my pen. That they are related exponentially, right? Now this exponent is 3 for ball bearings, right? And then 10/3 for roller bearings. Since we're going to be working with ball bearings, we can just use 3. So the force times the load to the 1/3 is constant. All right. All right. So here's an example that I would normally have you guys do with with your neighbor, but you can't solve by yourself. Think about this. Maybe pause the video if you want. Let's imagine your kayak trailer or your boat trailer or whatever has ball bearings. Not true. We already said they have roller bearings, but we'll use ball bearings. If you want to increase the life of your bearings by a factor of 8, what happens to the load your bearing can carry, right? So I want this to last longer, which means I probably have to, so I want it to last longer. Here's the life, which means that the load has to go down. All right. Okay, so I have this kayak trailer, but I'm willing to carry a little smaller load in order that my bearings last longer, right? So say I've got a really, really long trip. Well, I know that the force that I carry times the life to the 1/3 equals constant. All right, so if I'm going to keep my same bearings, then I need to say, well, as it is now, the load as it is now, times the life as it is now, has to equal the load, the lighter load, and that's going to be times the new life to the 1/3. Well, I know that. Okay, well, actually, I'm going to just solve this. I'm really interested in how does my new load relate to my old load. So I'm going to say that F2 over F1 equal, let's say I had to divide that, so I got to divide L1 over L2. L1 to the 1/3 over L2 to the 1/3. So F2 over F1 equals L1 over, well, I want that to be 8 times as long to the 1/3, right? And so that means that F2 over F1 equals, well, those cancel. And so that means it's 1/8 to the 1/3, which is 1/2, right? So if I cut my load in half, my bearings will last 8 times as long, right? All right, well, but I don't want to carry less stuff. I've got, my kayaks are the same and all my gear is the same, but I just want to go 8 times as long. So what happens to the basic load rating of my new bearings, right? So obviously, if I want to travel longer with the same load, I need some bigger bearings, right? So let's just say the current versus the improved. Right? So the current is F1 L1 to the 1/3 equals F2 L2 to the 1/3. All right. But I'm gonna change variables a little bit right here. More useful variables. I'm going to write it like this. I'm going to say that the rated radial force times the rated life to the 1/3 equals my design load times my designed life to the 1/3. Okay, so this is, let's see if I can squeeze this in here. Rated and design, right? So if I solve this, my rated force, right, which is really what I'm interested in, because I'm going to replace bearings, so I'm going to get bearings that are rated at a new life, equals my design load, or my design force, times the LD over LR to the 1/3, right? Did I do that right? Let's see. I had to divide by LR. Yeah, so LR is on the bottom. Okay, good. Now I want my design life to be 8 times, right? What my rated life is, right? Because I want it to be 8 times what it was before. So my rated force has to be FD times. Well, I want it to last 8 times as long. So 8 times the previous one, or the rated one, over the rated one, right? And so I can cancel that stuff out, or that's to the 1/3 still. So my rated bearings, or the rated force of my bearings has to be my design times 2, right? So if I want them to last 8 times as long, they've got to be twice as strong. So the basic load rating has to be double. So double. All right. So that's, I mean, if you're good at algebra in your head, then this is super easy. But if you're like me and you get confused, then it's nice to actually work through it. But I like to use rated and design when you're trying to pick this stuff up. All right, so this does not apply directly to your project, but I talked about it briefly before. So if I've got just some radial ball bearings, right, like kind of what we're using, but I've got some thrust load and some radial load, right? So this is the say we've got the skateboard example, right? So I've got I'm pushing really hard here, right? So that's the radial load. Nope, that's the thrust load. Shoot. So this is thrust. And then this is a radial load there, right? So if I've got those, I can combine them like this, right? And how does that work? If the thrust load is pretty small, relative, less than a third of the radial load, right? Ft over Fr is less than a third. Then I just say it's the same, right? The equivalent force is the same. Now, if I start to increase a little bit, such that I have a pretty big thrust load, right, over compared to the radial load, it turns out that this ratio here actually goes down, right? So that, and that's because it's, well, in some small ranges, this actually goes down because I'm spreading the load out over more rolling elements. And then finally, if I've got a really big thrust load on a radially loaded bearing, or a bearing that's supposed to be radially loaded, then I just multiply the thrust load times 1.176, right? Okay. And then, for angular ball bearings, you can see there's, these are intent. Whoop. Whoa, 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 whoa. So these are intended to be loaded at that angle there, right? And then so it's not quite as extreme, right? I'd rather have a thrust load on these. All right. Now, reliability-wise, remember way back when we started defining these things, we said that these are also it's when 10% of them fail. That's the load we're talking about. So 10% of them fail is percentage of failures is about right here, right? Whereas when half of them fail, it's about here, right? And so it turns out that the median bearing will last about 5 times so long. So this is basically 50% reliability. And so there was a quiz a while ago where I said, hey, in reality, be a Rayleigh distribution. Well, this is a Rayleigh distribution, right? You can't have a bearing that has negative life. That doesn't make any sense. So it has to be pinned at 0, right? And then it goes up. And it's a form of a Weibull distribution, or it's a special form of a log normal distribution. But it's kind of skewed to the right. There are some bearings that just by dumb luck are going to last a really, really long time, and there are a few that are going to fail early. But remember, we're rating really at this is the rated life here, right? And then this would be the median, right? And it turns out they last about 5 times as long. So with that in mind, we have, we can adjust it here, right? We can say the life will be, right? Well, what do we have going on here? This is the rated life, right? This is the basic load rating, and this is the design load, right? And so that's very similar to what we just did. Why is it 10/3 here? This should be 3 actually. So let's cross that out. Let's just make that 3. Okay. So FR is the application, right? So that's the design load. Design radial load. And this is the rated capacity. And then so what is this? This is an application factor here, right? Application factor. So the bigger this is, a big Ka reduces the life, right? A big Ka reduces the life. Reduces life. And then Kr is a reliability factor, right? And so that means the more, if we want this to be more than 90% reliable, we have to have some Kr adjusted there. So small Kr means shorter life. And then L is the rated life. Usually 90 times 10 to the 6th. No, I've seen them actually at 10 to the 6th, so let's get rid of this here. I don't know how that snuck into my notes. And then this is the design life. Right, and then so what do those factors actually look like? So the application factor, right? So if I'm dealing with pumps, electric motors, stuff that's really, really smooth, it's just 1.0, right? If I've got some gearing and it's like as these gears are engaged, we have somewhere between a 1.0 and a 1.3. Light impact would be something like an internal combustion engine, Harley-Davidson engine, maybe it's in here somewhere. So, well, yeah, let's say this is, let's see if I can pull this off. That's like a Harley-Davidson. Harley-Davidson motorcycle, right? But notice these all increase the application factor, right? So Ka reduces the life. And then what about the reliability factor, right? So if I want to be more and more and more and more reliable, I use a smaller and smaller and smaller and smaller reliability factor, right? So from table, oops, go back here. And then this is, what is going on? This is one of my worst recorded lectures of all time, I think. And then this here is from plot. Okay, and we'll put that like that. Okay. So then, you can, it's really just plug and chug to get the rated. And let's leave this, that's for a roller bearing. That's for a ball bearing there. All right. Make a note for ball bearings. All right. Now, one more very important note. Multiple bearing reliability. And this means that if I have two bearings, right, and they're each only 90% reliable, well, that means in the total is only 81% reliable, right? So if I'm trying to get up to 90, 95, 99% reliability, I need really high reliabilities on each one of those, right? Because if one of the bearing fails, the whole thing fails. And so that's very important to note. That if the bearings are to be identical, each bearing should have reliability equal to the square root of the total desired reliability. So, I mean, why is the square root? Because of this. Right? So the reliabilities have to be higher because square roots get bigger. Okay. And then, so bearings for your project, right? So the standard bearing dimensions are in table 14.1. And I've got that here, whereas table 14.1. And this gives you pretty typical bearing stuff. So here's a really light bearing, it's 10 millimeters in diameter. You guys can probably be on the order of 17 to 30 millimeters in diameter, right? And then it gives you the OOD for the different series, right? Obviously, the heavier series I go, the bigger the outside diameter gets, right? So it takes more room to mount this thing. And then it gives you all the other dimensions, right? The radii and the other dimensions there. And then we go down to table 14.2, right? Table 14.2, this gives you the load rating, right? And, oh, this is 90 times 10 to the 6th. Okay, this is for 90 times 10 to the 6th. I was wrong before. Read the fine print. And at 90% reliability. Okay, so then you can actually find the loads, right, for a given bore. What series is it, right? And the loads go up and up and up, right? Okay, so I think that might be it. Yep, that's it.